So today I'm going to show you something really interesting about floating point arithmetic. So let's just get started and create a variable called a equals 0.1 while b equals 0.2. And now if we do something like if a plus b is equal to 0.3, console.log the sum was 0.3, and then we can do else console.log the sum wasn't 0.3. Now if we run this, it seems like extremely obvious that the first situation will print, but if we run this, you can see that it says the sum wasn't 0.3. And this isn't just a problem with JavaScript. So if we run Python, in Python, let's just say a equals 0.1, b equals 0.2. If a plus b is equal to 0.3, print, I'm just going to say hello. Now, if we run this, it doesn't print anything. You might be wondering how a computer could get such a simple operation wrong, because we all know that 0.1 plus 0.2 is 0.3. And the problem with this has to do with how computers calculate. So to illustrate this better, let's just change this to something like integers. So we can say 1 plus 2 equals 3, and then we can change this to the sum was 3 and the sum was 0.3. So if we run node.js again, it says the sum was 3, just like you would expect. And the reason for that is because computers, as you probably know, store everything in ones and zeros, or in other words, binary. So it's basically the same as base 10, which we use, but instead of the ones place, the tens place, the hundreds place, it's the ones place, the twos place, the fours place, and the eighths place. For example, a would actually be, in binary, a would just be 1 because it has 1 here. But 2, there's no number 2 here, so it actually goes and becomes a 2-digit number called 10. And just to give it a better example, let's say 100, give us some more numbers like that. And I'm not gonna convert it manually, but you can. A good way to do this is using toString, so it makes it a string. By default, it's just a normal string, so it would just be 1153. But if you put the number 2, it also converts it to base 2. So if we do console.log a.toString and delete whatever is here, you can say that the number is 10010001. Now, binary can also be used to represent floats or fractions. So, for example, if we say 0.5, which in base 10 would be 1/2, if in binary that would be 0.1, because for base 10, the digits to the right would be the tens place, the hundreds place, and the thousands place. And for binary, it would be the twos place, the fours place, and the eighths place. So now we can go back to the original problem of why 0.1 plus 0.2 does not equal to 0.3, because the problem has to do with repeated digits. In binary, there's no way to represent 0.1 or 1/10 in a finite amount of digits, so it will be a repeated decimal that continues forever. But because a computer cannot store an infinite amount of digits, it just cuts them off at some point, and you end up with not exactly accurate decimal. Same thing happens with 0.2. It will be like that. So both of these cannot be represented correctly. So when you add them, it will not become 0.3. There's slight inaccuracies, and these accuracies still remain when you convert them back into base 10 to display it. So if we actually do this now, it will be 0.3 and then 00000 and a bunch of zeros, and then ends in 4. So until now, I have represented floats in binary with something like this. But the problem is, this isn't how actually the bits are stored in a computer, because there's no way to store a decimal point or the position of it. And the only way you can store it is to add a few more bits to say the location, but that's not actually that efficient. And the actual way to do it is kind of like scientific notation. So it will be something like 10.1.011 times 2 to the power of 1. This is how it's actually stored. And because this way, the decimal point will always be 1 behind will always be in here, so we don't need to store it anymore. And the standard for the format of storing this is the Ieee 754 format. So basically, let's give an example with 8 bits. Normally this would have 64 bits or 32 bits, but for this example I think 8 bits will illustrate it pretty nicely. So the first bit is pretty easy, it's just a sign. So basically what it is if it's 0, it's a negative number, if it's 1, it will be a positive number. Now the second part is a bit more complicated. This is the exponent. So what the exponent does is basically just this part. We don't need to store the 2 because we know always that it's a power of 2. So with the exponent, we don't actually just put 1 here as in like 0, 0, 1. What we do is that there's actually a bias because we need to allow for negative exponents also. And the bias is calculated like this. So 2k minus 1. 2 to the power k minus 1 minus 1. K representing how many bits is in the exponent. So for our case, we have 3. So this will be 2 to the power 2 minus 1, which will be 3. So basically, we take whatever number that's stored here, and then we subtract it by 3. And that's the actual value of the exponent. Because we are subtracting, so we can have negative numbers. To get the 1, so we add it by 3, and 3 in binary is 1, 1. So the actual number, I believe, will be 4. Yeah, 4 in binary, which will be 1, 0, 0. Now the final part here will be called the mantissa. And this is essentially a fancy way of saying this part of the scientific notation. Also, because it is a scientific notation, the first digit will always be 1, except when the number itself is 0. So this means that we don't actually need there to be a 1 here to store that bit. So we can basically infer that there's a 1 here. And now we only need to store the half that's after the decimal point. So what can be stored here is 0, 1, 1. And now we have an extra bit for a bit more precision. And advantage of using it this way is that so that you can have the same amount of significant figures. And by significant figures, I mean basically like the amount of precision which is stored in the mantissa. So for example, in regular mathematical or the representation in like this way, we can say that the amount of precision we need is 3 decimal points. But the problem with that is that if you have a number that's like a few thousands, 3 decimal points might be way too accurate. But if you have a number that's like something like 0.001, 3 decimal points might not be accurate enough. But with the mantissa, we can always guarantee that we have 3 or 4 or whatever, how many you want, significant figures, so it will be pretty accurate for all numbers of different sizes. Okay, I hope you enjoyed the video. If you did, and if you learned something, make sure to leave a like and subscribe, and I will see you next time.